So thanks everybody for coming back to the last talk of the day. Let me again take an opportunity. I think we don't thank the guys behind the camera often enough. I very much want to thank all the support we've been getting from Omid and Jesse and others, and also the semester-long organizers. Thanks everybody. And we've given some reminders. So after this lecture, there's a reception. So please join the Gather Town location, and we can chat in a more leisurely way. It's my real pleasure to introduce my colleague, Konstantin Tikhomirov, at Georgia Tech. He's going to talk about some recent very sharp results with Pierre Joseph on sharp Poincare and log-Sobolev inequality, so-called switch chain on regular bipartite graphs.
Thank you for the introduction. Okay, so I designed the presentation to be very friendly, so I will start with some basic definitions. So the object of this result is the set of deregular bipartite graphs, simple graphs. But for future, we will need, I will need the definition of multigraphs because I will consider sort of in parallel the configuration model. It will be important. So deregular bipartite multigraph on the set of vertices. We have n vertices on the left, n vertices on the right. We connect every vertex on the left to d vertices on the right, so that the degree of every right vertex is d as well. So this will be the object. If the graph doesn't have multi-edges, it's called simple. And we will have these two, this notation, this omega n of d. I don't know if you see when I select the text. So this is the set of simple bipartite graphs, and omega n with a superscript capital C configuration model, I will discuss this later, will denote multigraphs. The multiplicity will be denoted by mult of at the edge. And one small thing, the adjacency matrix, I'm not sure I will really need this, but the adjacency matrix will be viewed as n by n matrix for such graphs instead of 2n by 2n. So formally we'll have 2n vertices, but we can always reduce the matrix by removing the zeros. The zeros on the two minors consistent of zeros, so it will be n by n. So here is an example. If I have a multigraph on 4 left and 4 right vertices, here is the corresponding adjacency matrix. You see here we have a single multi-edge going from left vertex 3 to right vertex 4. Okay, so next definition is of simple switching. So we can define an operation for transforming a deregular graph. We start with bipartite multigraph and pick two edges, I1, J1 and I2, J2, such that multiplicity of both edges is non-zero. So the two left vertices, I1 and I2, are distinct, and the same for the two right vertices. Then we define the simple switching operation on these edges as the operation of replacing the original edges with I1, J2 and I2, J1. So we just swap the, you can view this process as swapping the endpoints of the edges keeping the same initial points, I1 and I2, you swap the endpoints. And this is the formal definition. It's just the transformation of multiplicities. We have decreasing multiplicities for edges I1, J1 and I2, J2, and we add multiplicities to I1, J2 and I2, J1. Everything else remains the same. Here is an example of the simple switch. Again, I start with the same multigraph on the left, and then I pick two edges, and then I just switch the right endpoints of these two edges. And you see what is the corresponding operation on the adjacency matrix. We just move one. So this 2 is decomposed. It's a multi-edge. So 1 is moved to this position 3, 3, and 1 at the top is moved to the position 2, 4. Okay, so we have now our objects, the operation for traveling on bipartite graphs. Now we can define what the switch Markov chain is. So we have this space, either it's simple bipartite graphs or multigraphs. And then we define, in both cases, we define the switch Markov chain as follows. So given a graph, we pick two edges independently, uniformly at random. And you see if we have ordered pair of edges, we have nd times nd minus 1 choices. So if the edge has non-trivial multiplicity, we pick this edge according to its multiplicity. So the number of choices is always the same. And then if the edges are not incident, in case of the multigraphs, we then we do simple switching on these edges and move to the new obtained multigraph. In the simple case, in the case of the space of simple graphs, we require additionally that not only the edges are not incident, we require that the simple switching operation on these edges does not introduce multi-edges. If it does not, then we again move to the next graph. Otherwise, stay the same graph tree. So this is the definition of this of the chain of the Markov process. And so for the simple bipartite graphs, it can be shown that the stationary measure is uniform. For the switch chain on the multigraphs, the stationary measure is not uniform. You see, it depends really on multiplicities of edges in the graph. So we have here this factor in the denominator, which is the product of multiplicities of the edges of G. And here 0 factorial is 1, of course, the standard convention. So both chains are reversible. This is just a useful observation for the future. So we have this reversibility condition. Here P subscript S and P subscript C are corresponding transition matrices for the simple graphs and for the configuration model that I'm going to discuss soon. Okay, so next I just want to set up the notation. It is a general setting. We have reversible irreducible Markov chain on finite state space omega, transition distribution P, stationary distribution P, transition matrix P. So by reversibility, we know that eigenvalues are real. We will order them in the non-increasing order. And then we will define the relaxation time as the inverse of the absolute spectral gap, and the mixing time as the first time when the total variation distance between the stationary distribution and the distribution of tth step of the chain, given some initial state omega, is less than 1/4, where this maximum is taken overall. So I will consider only mixing time with this 1/4 fixed without considering epsilon mixing. So we have this standard relation, which partially justifies why the relaxation time is interesting, can be interesting. Okay. So next is also general observation connection of the notion of relaxation time to Poincare inequalities. So again, if we have irreducible reversible Markov chain with Markov generator Q, which is transition matrix minus identity, we say it satisfies a Poincare inequality for every function from the state space omega to R. We have this inequality. The variance of f is bounded by these local fluctuations of f with appropriate weights. So where we use the generator.
Question,
yes.
I'm sorry, could you explain what is PT? It's a distribution at time t of what? Distribution of what are you looking at? I just completely don't understand.
So at the previous slide, you mean?
Yep.
At the previous slide, PT is so it is PT of omega is the distribution which encodes the transition probability. So it is a transition after t steps given initial state omega. So
transition
if x0
what?
if of the chain, if x0 is equal to omega, then conditioned on x0 equal omega, you have some conditional distribution of xt. Xt is the tth element of this chain, yes, tth element of the stochastic process. So the distribution of this tth element on the state space omega is usually denoted like this. So, okay.
I don't
so
quite understand what random elements. You don't have any random elements.
But here there is no random elements. It's just comparison of distributions. You have distribution of xt, and you have stationary distribution. It's just comparison of probability mass functions. Okay.
Yeah, Galina, just think of p to the t, the matrix p raised to power t, applied to whatever distribution you start with. Could be
and the transition matrix is just between the adjacency matrices, just like what are we talking?
No, it is transition matrix of the chain. So
Switch
it is
chain.
probability. The ij's element is the probability of going from I state to j state.
And the state is what? The adjacency matrix?
The state is the graph, or if you want to view yes, it's adjacency matrix. Yes, if you want. Okay. So, returning to Poincare inequality, there is a standard computation which tells that the best constant alpha in the Poincare inequality. So sometimes the constant is put on the left-hand side, but here it's let's put it here on the right-hand side of the inequality. Then it's just the relaxation time. So it's the same thing. So instead of studying the relaxation time, we will just consider the Poincare inequality, just a matter of notation. Okay, so now finally I can state what the problem is. The problem is, what is the relaxation and mixing time of the switch Markov chain on simple bipartite irregular graphs? Why this question can be interesting? So this is a natural model for graphs. Maybe undirected irregular graphs are more natural and more often used, but bipartite irregular model is also important. And the switch Markov chain is a standard way to generate random, uniform random, simple irregular graph. You start with arbitrary graph, you run this Markov chain for some number of steps, and then if you have a bound on the mixing time, you know after how many steps your resulting graph will be almost uniformly distributed. So if you are able to have a strong bound on the mixing time, you will be able to say that after a relatively small number of steps, you will generate a uniform or almost uniform bipartite irregular graph. This problem of uniform or almost uniform generation of this graph is actively studied because although this is a natural model, it's not that easy to generate, and there are open problems about optimal algorithms for generation, especially in the dense region. So this is the problem, and here is the conjecture. that for d between 3 and n over 2, the relaxation time should be of order nd, and the mixing of order nd log n. Okay, so this is the conjecture. This is the question I'm going to study. Okay. Now, before stating our main result, I need to say a few words about the configuration model. So before I introduced this state space omega n superscript c, the state space of multigraphs, and we have the switch chain. I just here repeat the definition of the switch chain for the state space. Here is the generator of the switch chain. It can be easily computed. But the stationary distribution is the distribution that I already described. So this formula here. So okay, so how we can interpret this Markov chain? In fact, there is a very nice way to view this random process, a very nice interpretation, which does not exist in the simple case. But let's consider this case of multigraphs. So the distribution, the stationary distribution corresponds to so-called configuration model of randomness on the set of multigraphs, bipartite multigraphs. Here is how the configuration model is obtained. So instead of considering n left and n right vertices, we consider n left buckets. Each bucket contains d points and n right buckets. So here in this picture, the degree d is 2 and n is equal to 4. So we have altogether 8 points on the left and 8 points on the right. Then imagine that we consider uniform perfect matching of left vertices with right vertices. And after that, after we define this, we generate this uniform perfect matching, we sort of compress back the buckets to the vertices. So this is what we get in this particular example. So the graph, the multigraph that we obtain in this way will be distributed according to this measure P subscript C, the measure that I defined on the previous slide here. Okay, so this is the configuration model. The advantage of this interpretation is that you can relate generation of, you can relate uniform random perfect matchings here on the left of this picture to just considering random uniform permutations of ND elements. And moreover, the switching operation on this perfect matching will then correspond to the transposition operation for the permutation. This way you have a straightforward correspondence between the switch chain on multigraphs and the transposition chain on the set of permutations of ND elements. So this is what what I just said. And this correspondence allows to compute the mixing time and relaxation time. Basically, you don't compute, you just say that the mixing time and the relaxation time is bounded by corresponding quantities for the transposition walk on the set of permutations, and those results are old known results from the literature. So here is the statement. For the transposition chain on permutations, optimal bound for the Poincare constant is known, and for log-Sobolev, for mixing time, it is known. It's the result due to Diaconis and Shahshahani. And once you have this result, it is very easy to relate this to the corresponding quantities for the switch chain on multigraph. So this is the claim. Poincare constant of switch Markov chain on multigraphs is of order ND. So the conjecture, if you recall the conjecture that I stated before, for the simple graphs. For multigraphs, it is, well, given known results in the literature, it's triviality. and also the mixing time of order ND log n. So there is nothing really to work on. Okay, but this argument does not carry to switch chain on simple graphs because of this problem. When we switch in the simple graph setting, we should always consider the possibility of introducing multi-edges. So we prohibit moves that introduce multi-edges. And sort of we can view this as some work. We can also view this as some work on perfect matchings, but not all perfect matchings, only those which correspond to simple bipartite graphs. And then some of the switching will be prohibited. So there is no correspondence to the transposition model for permutation. So here are some results from the literature. So I must say that the literature is so there are numerous results, a lot of results, but I would say that most of them deal with the undirected model rather than bipartite model. So here I mentioned two results on the bipartite model. So the result due to Cannon, Titali, and Vempale, the mixing time of the switch chain on the bipartite graphs. Here is the estimate, which comes, it was not stated in this form in the paper. So that paper dealt with the question whether this chain is rapidly mixing. And what the authors proved is that, yes, the chain, the switch chain on bipartite simple graphs is rapidly mixing. So this is just an explicit dependence on N and D that Pierre and I traced in the argument. And here is also explicit dependence on N and D with some variation of the argument in another paper by Dyer, Greenhill, Clear, Rosen, Stu. So a lot of papers dealing with undirected setting of directed graphs, graphs with predefined degree sequences. So here I mentioned some authors who were working on that or who worked on that before. But I would say that the primary direction now, although it's very active, is still rather about proving that the chain is rapidly mixing. Rapid mixing means that the mixing time is bounded by a polylogarithm of the state space from above. So it is more in this direction. So very general setting, very weak assumptions on the degree sequences, but as an outcome, rather suboptimal estimates on the mixing time. You see here, even here, the powers of N and D are really huge. Okay.
The result for perfect matchings, can you remind me? That's they prove that just by they just calculate the representations.
Yes, but I didn't really go into details. Yes, it was something like that. Yeah, I didn't read that paper in detail. Okay.
Also, there is, yeah, I'm trying to remember. So this can also be seen, the simple graph case, as given the row and column sums. I see, maybe not for the switch chain. All I wanted to say was there was a byproduct of Jerome Sinclair Vigoda result, right? Right. Maybe this is what James Lee was talking about. Perfect matchings of bipartite graphs. I think as a byproduct, they showed it is possible to sample from simple graphs given the degree sequences. Yeah, but it's not about switch chain.
Yes, this yeah. I also should mention that. Yeah, this is actually what mentioned here. So there are other methods apart from the switch chain, other methods of generation of uniform graphs, the regular and more general models. Yes, not using the switch chain. There are even methods for exact uniform generation, assuming some assumptions on the degree. If degree is not too large, there are fast and very efficient methods. Yes. But here we just work with the switch chain.
Mhm.
Okay, so another thing before I state our result is because this will be important in the last part of my talk, the canonical path method. It is used in lots of results dealing with this particular model, the switch chain. Here is just some example of the canonical path method. I wanted to give some example. It's not the only possible way to there are many variations, but here just let's see how it goes. We have some reversible reducible Markov chain, say with uniform stationary distribution. I just give an example. There are more general results. So for each pair of states, we choose some paths connecting x to y for each pair of states x and y. And then we can define this quantity, which can be interpreted. So this sum here, the sum in the brackets, can be interpreted as some way of measuring the length of the path. And the summation is taken over all paths containing the edge from I to j. So now we take the maximum and we normalize by the cardinality of the state space. And then there is this classical estimate that the second eigenvalue of the transition matrix is bounded from above by 1 minus 1 over kappa, with kappa defined this way. So the idea is the following: if you are able to construct for this canonical path in such a way that no edge is reused too many times, then you are able to get an efficient estimate on lambda 2. And some lower bounds on lambda n are also available. I just didn't write them here. So you will be able to estimate the absolute spectral gap and solve the relaxation time. Okay, canonical path plays some role in our argument, but it's sort of a part of the argument, not the main point. Okay, so yes, here is just some remarks that just apply and say this statement to our problem. Of course, it doesn't give the optimal bound on the Poincare constant that we want. Okay. So finally, I am able to state the result. You see, we have the assumption on D. We really worked hard to allow D grow to infinity with n. It was our intention to make the result work in this setting as well. But still, upper bound, you see, we have a very small power of n as an upper bound for D. So we have these assumptions on parameters. Now the statement is that provided that D satisfies this condition, the switch Markov chain on simple deregular graph satisfies Poincare inequality with a constant of order nd. With a constant of order nd. This is just explicitly written Poincare inequality here. So the restriction of D we did not optimize, but it's clear that in our argument it cannot be pushed to say anything close to 1. So we definitely have some absolute threshold when our argument fails. I think it's something around either 1/3 or 1/2. So above that, our argument really doesn't work. But some improvement is possible. So, and yes, the bound is optimal. The Poincare constant is really of order nd. And this can be checked by considering this simple function. You just define f of graph g equal to 1 if the edge 1 if 1 to 1 is an edge in G. Yes. First left vertex to first right vertex is an edge in G, and 0 otherwise. And you can check that with this function you really have this nd multiple. Okay. So, okay, let me just I want to see how much time is left. Okay, the approach. The approach is based on comparing this to the configuration model. We compare the switch chain on simple bipartite graphs to the configuration model. So how to compare? So just note that D goes to infinity, can go to infinity in our setting. So we cannot even claim that the total measure of this set of simple graphs in the configuration model is sort of does not go to zero. And so the measures P sub configuration and the uniform measure on the simple graphs really are incomparable in our setting. So okay. So assume for a moment that for every function from simple graphs to R, we can construct a function f tilde from the multigraphs to R, satisfying the following condition. First, the variance of f is less than some absolute constant times variance of f tilde with respect to corresponding stationary distributions. And second condition is for the Dirichlet forms. So suppose that the Dirichlet form of f tilde is bounded by the Dirichlet form of f for some universal constant. Then we would get the result because we know that the variance of f tilde is bounded by nd times the corresponding quadratic form of f tilde. And then we will just have this sequence of three inequalities, which will give us that the variance of f is less than some multiple of nd times the quadratic form, this quadratic form for f. So this is our intention to construct this function f tilde, but by itself, this is of course this is nothing. It's just our best wishes to find this function f tilde. The question is whether this function exists at all, and if so, even if so, how to construct it.
Kostya, is the first step where your assumption on the degree comes, or also in both steps? Because the two distributions are quite different, could be different based on multiplicities. The n to the 1 over 1000 that you mentioned.
Yes, the distributions can be different, yes, but still, do you agree that if we have these two conditions satisfied, then we get the result? Okay.
Yeah, this is it. Okay. But I was curious, I guess I shouldn't jump ahead, whether you need that assumption on the degree in both parts or only one.
I think more important is the bound for Dirichlet forms. This is really the heaviest part of the argument, and where we need very strong assumptions. For the variance, I don't remember exactly, but definitely assumptions are milder for the variance.
Thanks.
Okay. Okay, so this is some small remark about the harmonic extension. So you see the second requirement on f tilde. We need the Dirichlet form of f tilde to be bounded by the Dirichlet form of f. It suggests that the quadratic form, the Dirichlet form for f tilde should be small. Okay, whenever you, so if you want a Dirichlet form of your auxiliary function to be small, it seems natural to consider harmonic extension. So we start with the function f, which is a function on simple graphs. Yes, we view then this set of simple graphs as a boundary of the extension f tilde. So just define the harmonic extension. So this is the definition, the formal definition of the harmonic extension. It equals to the original function f on omega n of d, and otherwise it satisfies this this condition. And there is also some probabilistic, more explicit expression for f sub h. So the question is, if harmonic extension can be used in this context. So there is a problem with the harmonic extension because it can be checked that in the regime d go into infinity, you can construct an example of the function f such that its harmonic extension satisfies this. So the variance of the harmonic extension of f with respect to the configuration, to the stationary measure on the configuration model, is little law of the variance of the original function. Yes, and recall that originally we want both conditions to be satisfied. We want both the variance of f tilde to majorize variance of f, and at the same time the Dirichlet form of f tilde to be dominated by the Dirichlet form of f.
So this, what you just showed us, this just holds because you can find multigraphs that are very far from every simple graph, and they're, you know, and then just make the function large there, make the function 0 on simple graphs. So then the extension will have very small variance. Is that?
I should, I don't remember really what the example is, but I would say something like something like this. You should define a function f which sort of oscillates locally, but on the global scale it remains of the same order. And then if you define the harmonic extension of this function, this averaging procedure will kill local oscillation, and the harmonic extension will be almost constant. I will discuss this problem. We will have the same problem with our approach as well. But yes, I think this is the construction. Okay, so now I'm going to describe what the construction of the function extension is. So there is some reduction, which I don't want to go into it, some technical details, but in our assumption on D, you really shouldn't bother about multigraphs which have multi-edges of multiplicity 3 or greater, because the probability is very small. Really, we should care about multigraphs which have only multiplicity 2 edges. There are some other technical assumptions that are important. Okay, so here what we do, we start by defining this object called S neighborhood. S for simple, stands for simple. We start with multigraph G prime, and then for this multigraph, so we pick its multi-edges. So this ISJS is the set, the collection of multi-edges of this graph of multiplicity 2. Yes, we agreed that multiplicity 3 we don't consider and greater. So suppose there are k edges like this. So then we define a path on the configuration model, the path of length k. We say that the path is simple if, okay, so here is some technical condition, but basically what this condition says is that at each step, you apply simple switching operation to destroy this one of the multiplicity 2 edges. Okay, say if you start with k multiplicity 2 edges in the graph G prime, then after k steps, you destroy all of them and you get a simple graph. In fact, there are some additional technical assumptions, but for this talk, let's just assume that that's everything we want, just to destroy all multi-edges and to get to a simple graph. This way, we sort of get to the closest possible simple graphs. Of course, you can destroy multi-edge in many ways, right? You can pick kind of the other edge you switch with. There are many choices, so you will get actually a lot of simple paths leading from this graph G prime. So we have many simple paths of length k, and the set of all endpoints of this simple path will be called the S neighborhood, simple neighborhood of the graph G prime. So roughly speaking, it is the set of all nearby simple graphs. Okay. So now I will need this function. So this is just the averaging over S neighborhood. So for each multi, oh, I'm sorry that I should really use different notation. So this G prime now plays the role of G. So okay, the point is that this is an averaging over S neighborhood. For every multigraph, you define this function h of the multigraph as the average of the original function f over the S neighborhood of this multigraph. Okay. So this is some preliminary construction. Okay, so now this function h provides sort of some part of the extension f tilde that we need. H sort of plays the role of the harmonic extension, but it is better for us because it's easier to work with. Maybe if I have time, I will comment in the end why we use this notion of S neighborhood instead of just picking H to be the harmonic extension of F. But the same problem as with harmonic extension, H by itself does not work as the valid extension F tilde because its variance. It's okay. Its Dirichlet form can be nice, but its variance is not nice. It can be very small. So in order to construct extension with the right variance, we introduce controlled fluctuations to the function h. So how we do this? We start with auxiliary Gaussian field. So our construction will be randomized. So we construct an auxiliary Gaussian field on this configuration model. The field satisfying all of these properties. So let's see. So we have a function. We fix from the beginning function f on the set of simple graphs. And now we construct the Gaussian field on the set of multigraphs. Yes, the set of Gaussian variables indexed by the collection of multigraphs. So centered, variance of each component is equal to 1. And now there are two more conditions which are sort of contradictory to each other. The first condition tells us that for any adjacent graphs, multigraphs, the covariance of these Gaussian variables is large. So here I put some constant d over n, and this is what we use in the paper, but please don't pay too much attention. D over n does not really play much role here. There is some room for changing the constant. There is some valid range for choosing this constant for which the construction works. Just view it as the statement that the covariance of nearby variables is huge, is close to 1. So this is the first condition, huge correlation. The second condition, which is very technical and it's difficult to read, but basically what it means that the field should not be too correlated. So when we consider this field on the global scale, then the variable, say if we pick two graphs, typical graphs on omega n c, then these variables, psi of g1 and psi of g2, should be almost uncorrelated. And here, what is written here in condition 3 is just the precise statement of what exactly we want from these variables. So we want this complicated expression, which just appears in our bound of the variance. When we bound the variance, it is this condition becomes important. But just view it as the condition that the field is not too correlated on the global scale. Okay, pick two typical multigraphs. Psi of G1 and psi of G2 should be almost uncorrelated.
Can you do this just by taking a field that's just take the Gaussian free field, but grounded at like a random subset of vertices?
So we thought about using Gaussian free field, but since we don't have any experience with that, we ended up just cooking up some amateur construction. So no, we don't use Gaussian free field, but I'm sure it should be possible to use it. Yeah, but we just constructed sort of directly.
Yeah, I mean, the Gaussian free field would be the one which maximizes your variance subject to those covariance conditions on adjacent vertices. That's why.
Yes, probably something like this will work. But yeah, so as I said, we just use some other construction. It is also based on some randomness argument, some averaging argument. Okay. That's why I don't discuss why we know that this field exists, because I'm sure we can just use some advanced theory to show this very fast that such a field exists. So I just assume that it is constructed. Now, suppose that we have a function. Yes, we now define its extension f tilde by the following rules. So here I just to say in advance, I meet some cases, some technical cases. There are issues with some simple graphs which are not contained in too many S neighborhoods. I should say are contained in very few S neighborhoods. So there are also issues with the graphs that have multiplicity 3 or greater of edges. So some marginal cases which I really don't want to discuss here. Two main cases are explained here. If G is simple, then we just have f tilde is equal to f. It should be an extension. And if G is the multigraph, then first we define local variation of f. You see what this expression here means. It's just sort of local variance of f if you consider uniform distribution on S neighborhood of our graph G. Because H, if you recall how H was defined, H is nothing but the average of the value of f over S neighborhood of G. So we have f minus its average over S neighborhood, and we sum up the squares and normalize. So this is just the variance with respect to uniform distribution on S neighborhood. And now this is how we introduce these controlled fluctuations. So we take f tilde to be G, to be this averaging, plus psi of G, this element of the Gaussian field, times the deviation, times this local standard deviation. Okay. So okay, yes. So there are some special cases, but essentially this is how f tilde is constructed. So we have global averaging sort of, and so we have a part which is responsible for capturing global fluctuation of f, and we have this part which is responsible for capturing local fluctuation of f. Okay. So here is some graphical interpretation of what is going on. So this controlled fluctuations are needed to treat the following case. So imagine that we have a function f that has large fluctuations on the local scale, but globally remains constant. So how we can generate such a function? Just assign, say, independent uniform values in 0, 1, or just independent Bernoulli variables. Consider independent Bernoulli variables attached to each graph, each simple graph. Then you will have a function that on global scale is just the same. It's just the expectation of this Bernoulli variable. But locally, it will have fluctuations of order 1. So the variance of this function will be of order 1. This is how I graphically represent such a function. But now, if you just try to define its extension as the averaging H, as the averaging over S neighborhood, then this just kills the local fluctuations, and the resulting variance will be very small. So it's the same problem as with harmonic extension. But these controlled fluctuations with these parameters W of G, they actually resolve this problem. It turns out that they resolve this problem. Here is a statement, formal statement, summary of what happens. So if we have this function, we have this Gaussian field satisfying the mentioned properties. So we have f tilde as a randomized extension of f. Then with positive probability, we have the two conditions that we want to confirm. Yes, we have condition on the variance, and at the same time we have condition on the Dirichlet forms. And this basically this immediately implies the right bound on the Poincare constant. Yes, the bound on the variance is guaranteed by the condition that elements of the Gaussian field are not too correlated. That's what I said. On the global scale, they are uncorrelated. But the bound on the Dirichlet form is possible because the elements of the Gaussian field are not too uncorrelated. You see, here we may encounter the opposite problem, because if we make this size too correlated, then the fluctuation of our extension will be too huge, and the Dirichlet form just we won't be able to estimate the Dirichlet form in the right way. So there is sort of these two contradictory conditions that we have to satisfy simultaneously, and this sort of restricts very much the choice for the construction, for the extension. Okay, so I see that I'm almost out of time, so unfortunately I will have to skip the discussion of how how we go with this extension. So there is some canonical path argument that is used partially, and yes, and here to complete the talk, here is the another statement that we get. For constant d, we are able to get optimal bound on the log-Sobolev constant. And this basically follows the same strategy, but the extension is simpler in this case, because in the constant regime, we don't have to worry about introducing the controlled fluctuation. So the construction of the extension is much simpler. And yes, we have this bound n log n for the log-Sobolev constant, which implies that for the constant d, switch Markov chain mixes in time n log squared n at most, and the conjectured value is n log n. So we are almost at the conjectured value, but with extra log n. Okay. So yeah, this is everything I have time for. Thank you for that.
I have another question.
Yeah.
For perfect matchings, the mixing time is, sorry, let me see. I see. For perfect matchings, the mixing time is known to be correct, right? Order nd log n, like Diakonis Shachachani. And so, well, okay. So now I can ask the question. I mean, the way that they get that is actually to analyze the entire spectrum of the chain using representation theory. So then I guess you could, I guess, right. So now in your setting, you would be left to construct these f tildes, but now you would have to construct entire subspaces of them instead of just a single one. Given a k-dimensional subspace of f's with a uniform bound on the on the Poincaré constants in that subspace, you would have to construct the k-dimensional subspace of f tildes. That would be the analog, I guess. I'm just saying that would, one suggestion to take off the extra log.
Yeah, but another thing is that what we're working on now is to consider modified log-Sobolev inequality.
Yeah.
We actually have an idea, a working idea that should give the right bound n log n.
Because for the random transpositions, that's a softer way to get n log n, James. You don't need the full spectrum. The full spectrum n log n bound of Diakonis-Shachani is great because it bounds the L2. But to get relative entropy and total variation, you can get away with modified log-Sobolev. The log-Sobolev unfortunately won't give because the truth happens to be 1 over n log n. and so it gives the extra log. Yeah, but as he said, if they do the modified, that could give.
Yeah.
Great. First of all, thanks again. And so, any other questions, comments? And I do have a grave confession and correction to make, but let me see anybody. So, yeah, Kostya, thank you for citing our results. Usually, it's a very nice gesture and kind to quote one of the organizers. But I had to go back and check on my email. So, over the years, a couple of people had complained that there was a mistake in our paper, the one with Ravi Kannan and Santosh Vempala. And yeah, and at least for the deregular case, I thought everything was good. But as it appears, apparently theorem 4.1, to be precise, in our paper was incorrect. The way we go from bipartite graphs to perfect matchings and back, there was a mistake. Catherine Greenhill, who's an expert on this topic, among other things, is writing a nice survey paper. And so she contacted us recently to see, how exactly to phrase this. So yeah. So anyway, for people listening in, it's certainly better to appeal to the other result. Santosh tells me he and I, at some point, in the last 10 years, figured out how to fix what we had done for the deregular case. But I don't remember anything, and nothing appears in print. Yeah.
I see.
So, any other questions, comments? And I checked the draft of Catherine's article, and she included certainly your recent results in that. Yeah, so something to look forward to. So before I forget, again, we've made various announcements. So thanks to Omid, you don't even have to leave the room pretty much. You just click on what he posted in the chat, how to get together town with. There's a reception now with, of course, BYOB.
Thank you.